We'll start in 5 minutes, sir. Good afternoon, dear participants. Myself, Sandeep, Professor, Electronics and Communication Department, SMIT, Chittorga. Uh, for the second session of day 2, we have Dr. Santosh M Herur with us. He is working as an associate professor and head of the Department of Electronics and Communication in Jain Institute of Technology, Davangere. And he has completed his BA in electronics in 2009, MTech in digital electronics in 2012, and pursued and completed his PhD in 2021 in VTU Belgavi. He has 12 years of teaching experience and also having a 6 years of research experience. He has published more than 15 papers in the reputed international journals, and he also received 2 Best Paper Awards in the international conferences. Under his guidance, so 2 UG and 2 UG and 1 PG project has received KSST grants, and he's also received a certificate of grant in an Australian patent. He's also filed and published 3 Indian patents, and he's also a life member of a IST and IAENG. He worked as an external judge for the state and national level technical paper presentation and project exhibitions. He's also delivered the various expert talks on FSM design, IoT security, NAC NBA accreditation, and outcome-based education. He's also worked in a internal academic audit expert, and he is recognized as an international institution level NAC coordinator, NBA coordinator in previous institutes. Under his leadership, the Department of Electronics and Communication Engineering has got accredited by NBA for 3 years from July 2023 to June 2026. He's also serving as an IQSC director in JIT Davangere. He worked as a reviewer for many research papers submitted to various international conferences such as IEEE, Springer, etc. So over to Santosh Herur, sir. So please welcome, sir. So please unmute yourself, sir. Santosh, sir.
Yeah. Sir, am I audible now?
Yes, sir. Yes, sir.
Yeah. Thanks for the wonderful introduction, sir. Again, as sir said, so myself, Dr. Santosh Herur, HOD, Department of E&C, JIT Davangere. I would like to present on image processing and applications. Application means in terms of image corner detection approaches we'll discuss on behalf of 5 days national level online FDP on emerging trends in signal processing, image processing, and artificial intelligence. So welcome you all for my session.
Yes, sir. Please go ahead, sir.
Yeah. So is my second slide visible, sir?
Yes, sir.
Yeah. So this will be going to be an outline of my today's session. So first we cover up. So whatever we will be seeing, it will be with respect to image corner detection approaches. So we'll see some two of the traditional image corner detectors and some two the proposed. Okay, so where the work has been done on some machine learning approaches such as support vector machine and ANN, artificial neural network. So in this way, I would like to cover some basic image processing and applications. So normally we in the teaching fraternity, we will be knowing what is image, how to define image, and what are the fundamental approaches of image processing and all. So, but as this FDP is stating like emerging trends in image processing, so we'll see the application wise. The application wise, we'll see. So the outline is first we'll cover introduction, then objectives of image corner detection, importance of image corner detection, then solution approach for the same, and some objectives like support vector machine and then artificial neural network, these two being the machine learning approaches. At last, noise removal from images. It is a kind of pre-processing we apply for images. And then at last, results and performance evaluation of various corner detectors. So here we go with the first slide. Hope I'm still audible.
Yes, sir.
Yeah, fine. So now what is the computer vision or machine learning, and how to apply these CV techniques for processing the images in terms of detecting corners. In the next few lines, we'll see about the corner or the definition of corner, right? So first we'll see with respect to computer vision. So usually computer vision relies on image processing techniques in order to obtain the information required for tasks devoted to perceiving, sensing, and measuring the world around a machine vision system. Nowadays, the artificial intelligence or machine learning or computer vision techniques, and it's the development of the code, like with the help of Python and some other scripts, as well as MATLAB also. So the computer vision is in boom. So it started from around
recording in progress.
So it started from around 2012-13 onwards, the boom in artificial intelligence. So we can see there are many such techniques, and under that I am going to cover SVM approach and ANN approach. So what is computer vision? It is the one which relies on image processing techniques. Okay, so which is related to perceiving, sensing, and measuring the world around machine vision system. So what are corners? So by looking at an image, if we take a chessboard, okay, So for each and every white checks as well as black checks, there will be a corners, right? So for every square, there will be four corners. Exactly, we are going to detect. Okay, so we will be seeing how the corners, such kind of corners, will be identified in an image. So the features here, the features to be extracted or the features to be detected is corner. So like I think people might be knowing about edge detection. So you might have performed some mini projects or projects on image processing with respect to edge detection, but here it is corner detection. So the application is the image corner detection. So what are corners? How to define corners? Corners are the principal local features in an image. They are nothing but the points that may have high curvature and appear in the intersection of various brightness sections of images. So if we see an whole image, so in a human perception, we can see where are corners. But we have to just train in such a way that the algorithm itself should detect the corner. So how does it find the corners? It is with respect to the high curvature and appearance in the intersection of various brightness sections of images. So what is the supposed pixel? Okay, suppose a pixel is there, whether that is corner or not, how to detect. So there are some various techniques with respect to the changing things in the pixel, like if it is bright or dark, based on that its intensity we can say that that is the corner. Okay, so in the upcoming slide we'll also see that. So in several image attributes or in image features. So corners are not altered by means of illumination, and those attributes or features have the feature of rotating invariance. So they account only about minimum of 0.05% in the total pixels. So if we have 8 cross 8 image, if we have an image of size 8 cross 8, then out of 256 pixels, so hardly 1 or 2 pixel. Okay, so we can say that is the contribution of a corner. One corner will consume about 0.05% of a total pixel of a image, a whole image. So these have to be either identified or extracted without sacrificing image information. Image corner detection have the empirical value and plays a vital role in the scale space theory, image matching, motion tracking, stereo vision, developing 2D mosaics, pre-processing stage of outline capture systems, image related representation, and various other fields. Detecting corners has long been an area of interest to researchers in image processing. Why it is of so much interest for the researchers is it is a very minute feature. A corner is you can see 0.05%. 0.05% of the total pixel. It is a very minute feature. So if we are able to recognize such minute feature, and all the camera applications or whatever camera related applications are there, yeah, maybe it is your mobile phones or laptops or bioscopic, microscopic, whatever. Okay, so wherever there is to be detection, okay, with the help of camera or images, so there all we require a corner detection. So if the corners are detected, then we can also detect some other things. Say for example, in biomedical applications, to know where is the tumor or to know where are the particular diseases or leaf diseases and all. Okay, so first there should be a feature extraction technique, and the popular feature extraction techniques are like edge detection, corner detection, blob detection, etc. Okay, so hence it is a area of interest for so many researchers. Corner detection is a basic operation in any photogrammetric and computer vision. So the objectives of my presentation would be to detect the corners in image using machine learning approaches such as SVM and ANN, as I mentioned earlier. And second objective is to have comparison and performance evaluation of image corner detectors. So now only I'll say that there are some traditional image corner detectors. One is the popular one is Harris corner detector. Second one is good features detectors. Okay, so these two are the traditional one, and the proposed SVM and ANN we also do the comparison. Okay, SVM and ANN image corner detectors. These both its performance we will compare with the earlier one, that is traditional image corner detector approach. So this is the objective. So importance, like as I already said, the image corner, if it is detected, then we are like we have a more like image processing capacity is more for any camera based or image based application. So importance of image corner detection. So computer vision and its importance at present and in future. Already this might be known to each and everyone. This is a very basic slide, it seems. So computer vision is a field that includes methods for acquiring, processing, analyzing, and understanding images, and in general, it's a high dimensional data from the real world in order to produce numerical or symbolic information. Yeah, that is sort of information. So for example, in the form of decisions. Yeah. So examples of applications of CV include the systems for first, it can be controlling processes such as industrial robots. Second one, navigation, for example, by an autonomous vehicle or mobile robot. Third one, detecting events, say for example, for visual surveillance or people counting. Fourth one, organizing information, for example, for indexing databases of images and image sequences. Then fifth one is modeling objects or environments. For example, medical image analysis or topographical modeling. Sixth one is interaction. For example, as the input to a device for computer-human interaction. And seventh one would be automatic inspection. For example, in manufacturing applications, yeah, this is required. And at last, one of the most prominent application fields is medical computer vision or medical image processing to know what kind of diseases or what kind of such features have been detected and how to prevent or how to avoid in future its development. So this is what the importance of image corner detection. Remember, again, I'm speaking of about one such image processing application, that is image corner detection, and its importance where we find here. Already you might have gone through all these applications, say for example, detecting events. Okay, so for visual surveillance or people counting. So people counting in the sense now in the cricket stadium to know how much people are there, how much is the strength of that stadium. Okay, so to know that this corner detect with the help of corner detection or some feature extraction, we can know how many people were there for visual surveillance, any CCTV or camera based application. So let's move on to the next slide. To know about application and importance of again corner detection in computer vision. Yeah, a corner can be defined as the intersection of two or more edges. Yeah, so that is also possible. As I said, chessboards, right? So if we can see any chessboard, say for example here there is a chessboard. Okay, so we can see okay, so here the intersection between two edges. Okay, so once this edge gets intersected with another edge, there we form a corner. So that will be one definition. So corner detection is an approach used within computer vision. So used within computer vision systems to extract certain kinds of features and infer the contents of an image. So corner detection is frequently used in motion detection, image registration, video tracking, image mosaicing, panorama stitching, 3D modeling, and object recognition. So some challenges associated with the same thing is, so the problem of detecting exact point that describes the corner position in the case of a band limited system is of main concern for high accurate reconstruction. That means if we want to get a high accuracy of image corner detection, then there are some challenges like this to exactly know the position to detect such things. High accurate corner extraction is a complex process due to the altitude, position, and orientation of the camera with respect to the object. Second, maybe the interior orientation of camera. Third, maybe the fluctuations of the illumination. And finally, the camera optics also does matters. Yeah. So the conventional techniques for corner detection either attempt to estimate the second derivative of gray level variation, or those which apply some convolution based approach. So these things will be also covered here, during artificial neural network techniques, which I cover there. So there, the how the convolution based approach will be done, and in order to detect the corners, and what will be the accuracy, that all we'll see in the last few slides. So central to these kind of both approaches use some user defined threshold. Okay, so some threshold is required to know where exactly the pixel is a corner or it is not. So in general, there is no principled method to set this threshold. We can set any value between 1 to 255. So if it is a 8x8 image. So indeed, what may be considered an optimal threshold generally varies across a single image, any single image. So the solution approach, we'll see if it is any machine learning, it can be SVM, ANN, CNN, or any machine learning techniques. Okay, so here we can see what may be the solution approach to get detected with the corner in any image and displaying the same there. So first we need to start, and then the second step is capture and store image, and then we can apply pre-processing techniques. Like pre-processing techniques means application of filters, applying filters for captured and stored image. First, if there are any disturbances or any noises or some blurrings are there in a captured and stored image, to just remove, okay, such kind of any noises or unwanted things in an image, we have to go for pre-processing. Okay, you can use any filter. So that is called as pre-processing, and then the machine learning approach starts. So machine learning approach can be unsupervised learning or supervised learning. So unsupervised learning, in the sense, it is autonomous. Okay, so it doesn't depend on any one thing. Okay, so it by default, okay, by autonomous, it will does its detection. Okay, so it is predict output based on input only. So supervised learning means it is dependent on one supervisor and predict output based on input and output. Okay, so the difference between these two are this. Okay, so then after machine learning approach, that means any of a machine learning techniques or algorithm we use, once the corner, okay, once the corner is detected, so that is called as feature extraction. Okay, so the feature extraction is done with the help of machine learning approach, and then that feature has to be here the feature is nothing but corner. So the displaying corner detection will be at the last step before we end this. So this is the flow chart of detecting an corner in any image. So in most simple words, a feature is an interesting part of the picture. An image feature could be anything. It depends on the problem or the nature of the application. As I said, here only we can see in the three images, one shows edges, second shows corner detection, third one shows the blob detection. So we can go through every pixel of the picture and decide if the feature we are interested in is present there or not. Well, some typical features that people look for depending on the problem they are trying to solve are the following. So edges here, if we give an input called as chessboard, okay, the first output shows us this black screen. The output will show us the edges, the detection of only edges here, okay, out of this chessboard. But here we can see the red colored dots are all called as corners. And here we can see the blobs, okay, whichever is only black colored checks are there, those are treated as a, here the one which are circled with the green color is called as blobs. These are called as one more feature called as blobs. So edges, corner, or blob. So people may be interested in such kind of detection. Out of this, we can say the minute feature. The minute feature is nothing but corner. Just like the edges, corners are an important feature in an image. Traditionally, we define corners as the point where two edges intersect. In computer vision, the terms corner and interest point are commonly used interchangeably. An interest point is simply a point in an image that is well defined. They can be robustly detected with a high degree of repeatability. That means more iteration. If we develop a machine learning approaches, and if there are more, if we work for more predetermined approaches like iterations, then we can get high accuracy. So therefore, we can say that a corner is also an interest point. But an interest point may not necessarily be a corner itself. So for example, interest points may be a point that is local intensity maximum or minimum could be an interest point. The end point of a line may also be an interest point. A point located on a curve which has a local maximum curvature. This can be also an interest point. Okay. So some properties of corners are they have a high curvature among neighboring local points. Look at any red corner in the above chessboard here, the red colored one. So is nothing but a corner. Notice that those red points lie in the juncture of regions having different intensities. Here, wherever corners are detected, there are the change. Okay, so the intensities are changing here only at these points. So hence this should be the principle. This should be the principle of detecting corner. We have to just see wherever there are drastic changes in the intensity. There we can say that it is a corner. And something about rotational invariance. It is another property of corners. In simple words, we can rotate an image at any angle, but corners will still stay the same. Okay. So also the number of detected corners will also remain the same after rotation. Finally, people need to identify corners in the image because it has a lot of application in computer vision. So already this is covered. So as my objective was first to detect, okay, to detect the image corners or corners in an image with respect to two machine learning approaches. One is support vector machine. Second one is artificial neural network. So here we started with the first machine learning technique. So what is support vector, or how to classify the two data sets or data points, and what is the hyperplane or optimal hyperplane, and what is maximum margin, why that maximum margin is required, and how much it is important for any support vector machine, that we'll cover in the next 2-3 slides. So we all can see this figure 2. So here this figure 2 shows us the possible hyperplane. So now let's classify. Here there are two data points. Okay, one in a squared and another one in a circle. Okay, the circled is in blue and square is in almost red or brown, right? So now we'll see how to identify the hyperplane or the optimal hyperplane. So the objective of the support vector machine algorithm is to find a hyperplane in an n-dimensional space where n stands for the number of features that distinctly classifies the data points. All right. So to separate the two classes of data points, there are many possible hyperplanes that could be chosen. Here we can see this data point and this data point. If we can just draw, there is one hyperplane here, right? In the same way, yeah. So this data point and this data point, okay, if we match, then there is another hyperplane. In such way there are some 4 to 5 hyperplanes we can draw, okay, which are close to each other. There are the both kind of data points which are close to each other. If we draw lines, then that forms the hyperplane. Okay, so these are the possible hyperplanes, but which one will be the maximum margin? So which one will be the here we can see if we have a hyperplane. Say for example, there should be line drawn at here, one line here and another one line here. If we have such kind of maximum margin of a hyperplane, okay, if that much gap is there, then we can say it as a optimal hyperplane, and that is going to be more accurate. There, if we use such kind of SVM technique, then we can get a good corner. Okay, so the good feature. So maximizing, we can see here a point maximizing the margin.
What about
Maximizing the margin distance provides some reinforcement so that are more optimum, so that future data points can be classified with more confidence. So these are some examples of small margin. Here it is a small margin, and this is a large margin. If we draw one line here and another line here, okay, then the distance is more between these two lines. So it is called as large margin. And here, if we draw a line here, like this, only one line, and another line which is close to this here, then this is drawn here, and it will lead to a small margin. So which one is more efficient is here, the large one, the one which is having large margin is more efficient. So support vectors are data points that are closer to the hyperplane and influence the position and orientation of the hyperplane. Using these support vectors, we can maximize the margin of the classifier. So deleting support vectors will change the position of the hyperplane. These are the points that help us build our support vector machine. Hope some things have been made understood related to support vector machine. So here the algorithm which we can follow for image corner detection, so which is support vector machine image corner detection algorithm. Okay, so flowchart of SVM image corner detection, we can say. So the first step is capture and store image, and then RGB to grayscale image. We have to convert it into RGB to grayscale image, so that in grayscale image there will be only two color involved. One is black and another one will be white. Okay, so it is very easy for us if we do the image processing for grayscale image rather than RGB or colored image. Okay, so the captured and stored image has to be converted to grayscale image first, and then we have to go for assigning or setting some threshold value, which will be any value between 1 to 255 here. So it is on random based. So then the next step is read pixel and check intensity. So read pixel and check intensity. If there is more variation in the intensity of the pixel from one pixel to another pixel, then there should be some doubt whether there itself the corner is there or what. Okay, and hence there we have to focus more, and we should again extract more feature there in order to detect the corner. So for that purpose, SVM classifier is required, and predict corner. This SVM classifier and predict corner I'll explain in the coming slide. There is some explanation. And once corner is predicted accurately, properly, go for displaying such corners on an image, either with any red dots or green dots, like that. Yeah, so the explanation is here. To decide whether the candidate point is a corner, the region in the neighborhood of the corner is analyzed. Surrounding pixels are analyzed to check if they are brighter or darker than pixel being analyzed. So why we are going to check whether the surrounding pixel is brighter or darker? To know where there is a intensity change, the change in intensity, okay, from bright to dark or more brighter or more darker, it may lead to a corner. So this is done by checking if all the pixels are greater than pixel being tested value plus threshold value, or smaller than pixel being tested value minus threshold value. This is the only key point with the help of SVM, how to know the pixels are greater than, the pixel is a corner or not. So first one is whether the pixel which we are detecting, if it is, that means if we are testing that pixel being tested value plus threshold value, okay. So if it is greater than this formula, or if it is smaller than pixel being tested minus threshold value formula, then we can make a detection like judgment. It might be a corner. The value of neighboring pixels is chosen. And if point P is a corner, then few pixels must be brighter than pixel being tested value plus threshold, or darker than pixel being tested value minus threshold. When both conditions are not satisfied, then the point cannot be a corner. So only these two conditions, okay? We have to check for only these two conditions to know the corner, okay? Either more brighter or either more darker, okay? So if both are not true, not satisfied, then it will not be for sure a corner. So thus this test can be used to reject corners as well. If all these criteria are satisfied, then we test the entire line segment. Hence, given a pixel point P and image matrix, we need to quickly identify the location of the corner detection. So location of the different neighboring points. So these relative coordinates from the center pixels are stored in a vector and can be used to obtain corner. So let K be the neighboring pixel. If K minus P less than minus T, let K be the neighboring pixel. If K minus P less than minus T, where T is nothing but a threshold, okay? K is a neighboring pixel and P is a corner point. If this is the case, so if K minus P is less than minus T, we will label the pixel value as 1, and if K minus P is greater than T, we will can also take values from 0 to 255. Thus the minimum value of K minus P, if K is 0, and P is 255, okay, then it will be minus 255. The minimum value will be minus 255 and the maximum value will from minus 255 to 255, which satisfy the condition K minus P less than minus T. Value 1 is assigned, and for value of K minus P which do not satisfy both the condition are assigned value 0 in the lookup table. Consider that value K and P are given. Does that means the value of K and P are given means in the sense in the with respect to 0 to 255, any value. Okay. So thus the task is to compute the index K minus P and look up the corresponding values from the lookup table, whether the condition, the corner detection condition is satisfied or not satisfied. One satisfies, then we can say corner is detected, which doesn't satisfy, then the straightaway corners are rejected or not detected. So thus given pixel P of X comma Y, we need to derive all the pixel using relative offset and look up their corresponding values from the lookup table. We have the pointer to the location of the pixel, this P of X comma Y. Let X and Y offsets be denoted by the offsets of this pixel be dx comma dy. Then the location of offset pixel will be determined as pointer value plus dy into columns plus dx. So this is the how to get the location of offset pixel. Thus a simple check of pixel labels is performed to reject invalid corners. The aim is to check if a neighboring pixel with labels either 1 or 2 is observed. This is the only aim. Okay, if it is observed, then there is a corner detected. Otherwise, it is no corner. So this is performed by process of elimination. The following pair of pixels is checked. If both of elements of any of pairs are 0, then it cannot be a corner. If all the tests are positive, we need to check if we obtain a continuous sequence of 1 or 2. Okay. If we obtain a continuous sequence, then corner is detected. Otherwise, not detected. So this will provide a list of corners. Then typically a corner filtering operations is performed after corner detection. The aim of corner filtering is to retain the significant corner which is spaced at minimum distance from each other to avoid clustering of corners at some location. So if we get the neighboring pixel value as like continuously in our test 1 2 1 2 like that, okay, sequence, okay, in a sequence, in a continuous sequence, then there may be side by side, we can't say corner if on a line or in just a change of one edge to one another edge intersection, there should not be two corner. Okay, there should not be 2 3 4 corners, there should be only one corner. Okay, so to avoid such clustering of corner detection, then we have to use some filtering operations at the same location. So in the present implementation, we have no measure to indicate a strong or weak corner. In Harris corner detector and good features corner detector, the eigenvalues of the matrix indicated strength of corner pixels. Thus, whenever a corner is detected, we need to compute a measure which indicates the strength of the corner. The response function used in the present application is sum of absolute differences of the pixels in neighboring arc and center pixel. Here, this is the response function R of X comma Y is equal to summation of P, which is belonging to this I of P stands for center pixel and minus arc of I of X comma Y. It is called as the pixels in neighboring arc. So the difference between this and this, the module of that, absolute difference of that will give us the response function. The algorithm's accuracy can be improved by pre-processing the data. That means upon applying the filters, okay, we can say the algorithm's accuracy will be, that means the number of corner count, the corner detection count will be improved based on the application of pre-processing. In that way, we can measure the accuracy. So one graphical user interface. So this figure depicts some options here. Say for an application, this is one image processing application built up here. Suppose we can have a click over all these GUI buttons. So this GUI, which is observed and are depicted in this figure 5 has how much buttons? So totally there are some 10 buttons. So one is giving us the display preview. Second one is to stop preview, and then capture image. Okay, and then so this is to see. Okay, your any Raspberry Pi camera or your mobile camera. Okay, when you turn on that camera, then it is under display preview. So then to stop it, then you can click onto that stop preview. And if you want to capture an image, you can click on this so that image will be captured. Then after capture image, so if you click on this CD underscore Harris, then it is CD stands for corner detection. Corner detection. CD underscore Harris. It is the Harris corner detector output. It will show you that output. Then CD underscore GD FTRS. That means good features corner detector output you will get at last. Okay. So CD underscore SVM means it is a proposed. SVM and ANN is a proposed method. Okay, proposed image corner. This Harris corner detector and good feature corner detector are the traditional one. SVM and ANN are the proposed one. Okay, so if we click on this, then we will get SVM output. If we click on this, then we will get the corner detection output of artificial neural network algorithm. And there's some more buttons. If you can add some noise. Say for example, salt and pepper noise. If we can add dots, right? Salt and pepper, black dots and white dots are called as salt and pepper noise. We can add with some probability 0.01, 0.05, 0.1 like that. So that can be also added and tested whether your image corners which is being detected are accurate or not, or if you are adding noise in an captured image, then also whether your algorithm is able to detect corners efficiently. To test the developed algorithm efficiency, we can add some noise, and then later on we can apply filter and then remove that noise, and so this is called as pre-processing, and then we can get the filter output, that means the corner detection output also. So this is PSNR. This PSNR stands for signal to noise ratio. Signal to noise ratio, and another one is entropy. Entropy will give you the the strength of the information. Entropy is measured as the strength of information which is present in an image. So yeah, so all these buttons I already explained there. So, but still we can just see display preview. When this button is pressed, the camera starts streaming live images. Stop preview, camera stops streaming live images. Capture image, when this button is pressed, live image is captured. When this CD underscore Harris button is pressed, Harris corner detection algorithm works on captured image and displays corner detected output. The same way for good features, SVM, ANN. And then noise, when this button is pressed, salt and pepper noise is added to image and noisy image is displayed. And there itself, median filter is applied to noisy image, and filtered image is displayed. Okay, when we apply median filter, then it washes out all these salt and pepper noise in the image with the noise, and then the filtered image will be the output of that median filter. We'll see the working principle of median filter in the later slides. So PSNR, when this is pressed, the signal to noise ratio algorithm works on captured image and outputs such as mean square error and PSNR results. Entropy, when this button is pressed, entropy is calculated. Remember that entropy will give us the strength of image information. So already we saw the working principle of support vector machine, SVM, support vector machine we saw. So we can just say that, conclude that this will be the result. Okay. So when we press on all these buttons, when we press up to display preview and then capture image, and then once I press on Harris, CD underscore Harris, so this is the captured image. Okay, this is the captured image, and then this is CD underscore Harris result when we press on this, and then when we press on this CD underscore good features, then this is the result. And when we press on CD underscore SVM, means support vector machine, that is proposed SVM result, we will get here. Okay, so so this figure 6 below, this is the corner detection in captured image without noise. Okay, so this figure below shows results of various image corner detections for real-time captured image through Pi camera, Raspberry Pi camera, without any sort of noise, without any addition of noise. Results include traditional corner detection methods. Results include traditional corner detection methods such as Harris corner detection and good features corner detection, along with the proposed corner detection methods, that is SVM. Okay, so now I think it may not like here in this Harris result, some green, like some here and there green dots are there. Those are detected to be as a corner in the captured image. Okay, and in CD underscore good features, again there are some less number of such green dots which are again treated as a corners. Okay, so in CD underscore proposed SVM underscore result, here also we can see some lots of green colored dots which are called as again corners. So with respect to the performance analysis of detected corner count for captured image, Harris corner detection shows in this image 71 corner, displays 71 corner, or detects 71 corners. Good features corner detection will display only 36 corners. Proposed SVM corner detection, okay, will show us more corner features are extracted here. Yeah, and here the figure 7 again shows for some other image which is not a real-time image. The previous one, this is a real-time captured image, the image captured by a Raspberry Pi camera. So this one is a inputted image. Okay, this is a standard image. Okay, image from a image database, standard image database. Okay, it is the house image. So for this image, we got Harris corner detection corner count is 36. Good feature corner detection count is 23. Proposed SVM corner detection count is 69. So one type of machine learning approach is over. So I think this is one way of detecting corner using support vector machine and its proper understanding. And next, another one approach is artificial neural network. So artificial neural network. I think Dr. Siddesh KB sir is going to deliver a session on artificial intelligence tomorrow or day after tomorrow. So he may also cover this artificial neural network or artificial intelligence techniques in his presentation also. So what I'll do, quickly I'll cover this ANN, which are very important and has to be delivered as of now. That we'll see. So we can see in artificial neural network, this figure 8 shows us the schematic diagram of this A is biological neuron and B shows us the artificial neuron. So why we call this as the artificial neural network? Neural network means it is the structure, the schematic diagram of artificial neural network is somewhat similar to our biological neuron, right? Those some inputs are there. Okay, some input signals are there, and based on some measurement of our brain or mind, as per the biological neural system, it will produce some of the output. Okay, many inputs, some output. Okay, in the same model, this is analogous. Okay, both are analogical to each other. So there are many input signals as seen in this figure, x0, x1, these x1 so on up to xn are the many input signals to the neuron. This is the neuron, okay, J, and we'll add a weight, okay, we'll add a weight to each of the signal. So each input is given a relative weight, W is equal to W1, W2, so on up to Wn, which affects the impact of that, particular input signal. Weights are adaptive coefficients within the network that determine the intensity of the input signal. The neural output signal. So here the Xj is here Xj is called as neural output signal. NET is produced by the summation block. Corresponding roughly to the biological cell body and adds all of the weighted inputs algebraically. Several kinds of ANNs have been developed, but two main categories can be easily recognized depending on the way of learning process. So one is supervised learning and another one is unsupervised. So already I said about the supervised learning and unsupervised learning at the starting few slide. So here we can say, yeah. Quickly, let's see under the supervised learning algorithms, what is going to be the structure of MLP. Okay, so that is multi-layer. MLP stands for multi-layer perceptron. So this figure we can see, figure 9 depicts the schematic of three-layered feed-forward neural network with one input layer. So this is the input layer. The another one is called as one hidden layer, and at last one output layer. So can we see this diagram? It is called as feed forward. Okay, it is a unidirectional. It is not a bidirectional. Okay, from left hand to right hand side, the flow is there. So it is called as feed forward. It is going forward. Okay, so many inputs are there in the input layer, but in output layer only few outputs are there. Okay, exactly what I explained here in that model. So this is going to be the structure of MLP. It will be having the input layers with many signals. It is having some of the hidden layers, and then with the sum of the summation blocks, and at last it will be having the output layer with very few output signals. So there is something called as backpropagation algorithm. So we have to use this backpropagation algorithm so that some more number of iterations can be done in order to get more fine tuning of the corner. More and more accurate corners has to be detected with respect to ANN. Then the backpropagation algorithm. So the MLP learning algorithm or backpropagation algorithm involves, so it involves the multi-layer perception learning algorithm involves a feed propagating step followed by a backward propagating step. So overall backpropagation learning algorithm in the MLP is given as below. So the overall MLP shows all these 11 steps, where the first step is randomize the weights W to small random values. Okay. So second step is select an instance T. Select an time instance T, a pair of input and output patterns from the training set. Then third step is apply the network input vector to network. Then fourth one is calculate the network output vector Z. Fifth one is calculate the errors from each of the outputs K. Okay, so calculate the errors from each of the outputs K. What is nothing but error? It is just as good as the difference between the desired output and the networked output. Okay, what is the desired output minus networked output is called as error. We will get to know the error. Calculate the necessary updates for weights in a way that minimizes this error. If there are more error, okay, if the error is high, then we can go for updating the weights in the way that minimizes error. That means we can still more randomize the weights at the first step we are doing, right? That the same kind of stuff. So then add up the calculated weights updates to the accumulated total updates, and then repeat step number 2 to 7 for several instances comprising and time. So then adjust the weights W of the network by the updates. Then go for steps, repeating of steps from 2 to 9 until all instances in the training set are processed. So this constitutes one iteration. Okay, from step number 1 to 10 will give us one iteration. Okay, that means step number 1 and then 2 to 7 and then 2 to 9. This whole procedure is itself gives us the one iteration. Please repeat such kind of iteration of steps 2 to 10. Steps 2 to 10 iterations we have to repeat until the error for the entire system of image corner detection is acceptably low. Error is very low. So up to that level, we need to do the iterations or some predefined number of iterations is reached. So if while going for image corner detection with the help of ANN algorithm, let us ourselves, we will have some predefined number of iterations such as 20, 30, like that. Okay, 100 iterations like that. Okay, we can execute for all such number of iterations as well. Or until best of the best corner is detected, we can go for the iterations. So here is the ANN, okay, artificial neural network image corner detection algorithm flow chart. So if we go through this image through this flow chart, there is something called as convolution operation. Okay, so when we start, the same kind of capturing and storing image should be done, and then input image we will get. Okay, on that input image we have to do some convolutional procedures. So convolution operation, then convolution feature map, then pooling operation, pooling feature map, fully connected neural network, and corner detection output. Here we'll get the corner detection output, and then we have to display that accurate number of corners must be displayed here. So we'll see between input image and corner detection output, what are the some 3 to 4 steps are there, that we'll see here. So the convolution. So what is convolution? So here we all know about the convolution, right? In our digital signal processing or signal system, we know it is generally multiplication. Multiplying two signals will give us the convolution, right? So when a new function is produced by mathematical operation of two functions, it is called as convolution. This new function reflects to which extent the original functions match if their graphs are aligned with each other. As per the convolution theorem, the Fourier transform of a convolution is a pointwise product of Fourier transforms. Convolution in one domain, say for example, time domain, equals pointwise multiplication in the other domain, that is, for example, frequency domain. So it's all the theoretical aspects of the convolution. In one dimension, the convolution between two functions is defined as follows. It is a standard equation of convolution. G of x is equal to f of x into h of x. So that is equal to integration from minus infinity to plus infinity, f of s into h of x minus s into ds. Okay, where f of x and h of x are two functions, and here wherever we use the s variable, it is a dummy variable of integration which takes value 0 or 1. So in the two dimensions, the convolution between two functions is defined as follows. So it is g of x comma y. Okay, previously it is only x in one dimension, now it becomes x comma y. So is equal to f of x comma y into h of x comma y. That is equal to, here it was single integration, now it becomes double integration from the same limit, minus infinity to plus infinity, f of s comma t into h of x minus s comma y minus t into ds dt. So here one more variable is added, that is t, and y is there. Okay, so an asterisk into, or this asterisk sign is used for convolution operation. So in an computer applications, the time series data will be discretized, and the time index t can take only integer values. Thus, the discrete convolution can be hence defined as follows. This is also the standard convolution, discrete convolution formula. S of t is equal to x into w of t is equal to summation of minus infinity to plus infinity x of a into w of t minus a. This is a discrete digital convolution. Yeah, so here this figure 11 shows us the block diagram of convolutional neural network. That means now whatever here step was there, convolution operation, convolution feature map, pooling operation, pooling feature map, fully connected neural network is now converted into this figure, block diagram of convolutional neural network. Now let's see the explanation of this block diagram so as to get the output of corner at the end. So yeah, in machine learning applications, the input is usually a multidimensional array of data, and the kernel is usually a multidimensional array of parameters that are adapted by the learning algorithm. Here, I stands for image. In this formula, I stands for, or here I stands for image, and K stands for two-dimensional kernel. K stands for kernel. Okay. So these multidimensional arrays are referred as tensors if there is a two-dimensional space. For example, image I as an input and the two-dimensional kernel K has to be used. The convolution for two dimensions is as follows. If we have a consideration of image I and a two-dimensional kernel K, then this is the equation S of I comma J is equal to I into K of I comma J is equal to summation M and summation N. Okay, I of M comma N, then K of I minus M comma J minus N. This is going to be the equation. So now this block diagram consists of input layer, then convolutional layer or convolution stage. So already we covered about the convolution stage or convolutional layer, right? So then next step is nonlinear layer or detector stage. So exactly here, the detection of corner starts. That stage we reach. Then pooling, it is also called as downsampling or subsampling layer, and then fully connected layer. So, and then we'll get the output layer. So this here at this stage, we can get some corners as the output. So here input layer is a multi-dimensional array of data where data are fed to the network. Input data can be image pixels or their transformation. A convolutional layer is the main building block of network. The prime purpose of this layer is to extract distinct features from input such as corners, edge, contrast, sharpness, etc. Right? So already we saw about the convolutional and its equations. The first layer extracts meaningful features such as edges, corners, textures, and lines. Next, convolutional layer extracts higher level features, but the highest level features are extracted in the last convolutional layer. Kernel size here K. Kernel size refers to the size of the filter which convolves around the feature map, while the amount by which the filter slides is the stride or step. Okay, so this is the meaning of step or stride. It controls how the filter convolves around the feature map. Therefore, the filter convolves around the different layers of input feature map by sliding one unit each time. Another essential feature of neural nets is padding that gives option to make input data wider. So nonlinear or detector stage. Okay, here the nonlinear or detector stage, third step is used to detect each linear activation through nonlinear activation function. So there are several nonlinear activation functions. The standard way to model a neuron's output f as a function of its input x is with f of x is equal to tan h of x or sigmoid or rectified linear unit. So the why sigmoid function? Why here sigmoid of x is required to know the standard to model the neuron's output f is just for the simplicity. It is very simple to model as a neuron, and this makes training several times faster. The pooling layer makes it robust to small variation for previously learned features. Pooling makes sure that network focuses on important pattern. A pooling layer produces downsampled versions. Here the pooling is also referred as a downsampling, which that pooling layer produces the downsampled versions of the input map, whatever input image I is having. So it's a downsampled versions is produced, and it reduces the dimensionality of the feature maps used by the following layers. Okay. So in general, or all in all, we can write one formula or equation called as xj L, okay, xj to L is equal to f of summation I, which belongs to mj, xi of L minus xi L minus 1 into kij L plus bj L. So here, what are all these stand for? So what we are seeing here, this is discrete convolution. Here we are seeing discrete convolution. I think it is in the form of discrete convolution formula. S of t is equal to summation of minus infinity to infinity x into w. In the same form, this formula is there. As we are applying image as an input, okay, we are applying image as an input. Image is a discretized signal in terms of converted to a gray level, ones and zeros, right? And then here, this formula is treated to be as a discretized convolution formula. So where L here in this formula, wherever L is there, that depicts the convolutional layer. Wherever there is L minus 1, that is the downsampling layer. Then here xi L minus 1 is there. It shows us the input features of L minus 1 convolution layer. Then here KIJL stands for kernel maps of L convolutional layer. In the same way, BJL shows us the additive bias of L convolutional layer. Here MJ, I belongs to MJ is there. So that MJ represents a selection of input maps. And then I and J, okay, those are called as input and output. So I is input and J is the output. Ith input and jth output. Yeah. So this is how we can just become familiar of this flow chart of ANN image detection, image corner detection, or image processing, and this block diagram is simplified in terms of this formula. Same way, like we got SVM output. Now we'll see Harris corner detection and good corner detection. And now if we press on the ANN proposed a corner camera without any sort of noise. Results include traditional corner detection methods such as Harris corner detection and good features corner detection. Hello, sir, am I audible?
Yes, sir.
Yeah, okay. So along with the proposed corner detection methods, here the proposed method is artificial neural network kind of corner detection. So again, already this image we saw earlier, and for the same image, when we do the processing and detect some corner feature here, then we can say some more number of green dots, which are nothing but the corners. In comparison with good features corner detector and Harris corner detector, we can see here Harris corner detector gives us 71 corner. Good feature corner detector gives us 66 corners. Proposed ANN corner detection is giving us result of 274 corners. And in the same way for already the image database the image from the standard image database, that is house image. In the same way, we'll get 36 Harris corners, and then 23 good feature corners, 23 only, and proposed ANN corner detection. So we can see here the green dots. Okay, total it is 111 corners detected here. So I think this was my main agenda, like image processing and applications. So we saw the image processing with its application to be as image corner detection approaches. So these are going to be some 4 image corner detection approaches. One is Harris corner detection. Second one is good features corner detection. Third and fourth one is the proposed one, that is SVM and ANN. So that is all enough, it seems. So here in the upcoming slides, we have some application of pre-processing stages, like applying some filters called as non-linear filter, which is a median filter. Okay, so here we have used a median filter to do some pre-processing and to just have a more clear picture, more cleared image. Okay, without noise. If there is any sort of noise in a captured image, to remove, just to have a removal of such noise or any noise, if any, right? We can use such kind of filter. Okay, this is median filter. It is a non-linear filter. Why we use filter is to just remove any noises are there. Okay, so the input for this median filter will be the captured image or input image. Okay, so the output of this median filter will be the noise removed image. Okay, the image with no noise. Okay, if any noise was there, then it is been removed and only the clear image is present at the output of median filter. So this is the working of median filter. How if we have this 3x3 matrix based image, say for example, if this Cx comma y, if this AT, if this AT is a central pixel, okay, out of these 9 pixels of 3x3 image, if this AT is determined as a central pixel, then that central pixel has to be now replaced with the median value. Okay, median value. So we need to compute W median. Okay, that means the median of a pixel values in window W. Okay, so window W is of 3x3, and here what values we are having, that we need to write in an ascending manner. Okay, so 3, and then ascending value is F, and then 8, 10, 11, so on up to the highest value is 80. Okay, so that is written, and the middle value, the mid value of, if there is a 9 values here, then obviously fifth value is going to be the median value. Okay, and here the median value 3, 5, 8, 10, 11, 14, 20, 22, 80. Out of these ascending values of these 3x3 values, the middle value is determined or found to be as 11. Okay, so this CXY, that is the central pixel, that is 80, must be replaced with this 11. So the second step is compute W median. The W median is 11 now. So third step is replace CXY by, that is central pixel 80, by W median, that is 11. Here 11 has to be written, and repeat steps 1 to 3 until all the pixels in the entire image are processed in the same manner. So yeah, so central value it is replaced by 11, and it is easy to implement. This median filter is easy to implement and is used for denoising different types of noises. Median filter tends to remove image details while reducing noise such as thin lines and corners, or as such. So some 3 parameters are there to understand related to noise. So one is PSNR, that is signal to noise ratio. This is the signal to noise ratio formula, 20 log of max F divided by root of MSC, where MSC stands for mean square error, where MSC mean square error is equal to 1 by Mn into summation 0 to M minus 1, summation 0 to N minus 1. Okay, so F of double modulus of F of K comma L minus G of K comma L whole square. Okay, so this is mean square error. So what is the relationship between noise, okay, signal to noise ratio, and mean square error? It is inversely proportional. PSNR is inversely proportional to square root of MSE. So if MSE keeps on increasing, if MSE mean square error of any image, okay, upon application of filter, okay, if there is a mean square error, and if the mean square error keeps on increasing, then the signal to noise ratio keeps on decreasing, right? So signal to noise ratio keeps on decreasing, then that means noise is decreasing. Okay, so this is the relationship we have to just understand here. So entropy, as I said, is a measure of image information content. Entropy is a measure of image information content. Let's not bother about the formula right now here. So directly we'll dwell into the results. So here, this shows us the, yeah. So this shows us the results with real-time captured image. That is corner detection in a captured image with denoised image. Okay, so with denoised image means we have captured the image, we have captured the image and we have added the noise. Okay, we have added the noise artificially, or here the noise is salt and pepper noise. So we can see dots, right? So white dots and black dots are there, which are nothing but the salt and pepper noise. So with the noise probability is equal to 0.01. Okay, this is the noise image. Okay, captured image we all know now. This was our previously captured image, right? Real time Raspberry Pi captured image. Okay, so now for that captured image we went for adding the noise button was there, right? So by adding that, by clicking on that noise button, we have given the noise probability of salt pepper noise as a 0.01. So that 0.01 means some less noise will be added. Okay, so we can see here noise probability is increased from 0.01 to 0.05. So more salt and pepper noise is added here. Okay, in the same way, some more, if when we raised noise probability is equal to 0.1, then we can see the image full of black and white dots. So it is called as, sorry, black and gray dots. It is to indicate the noise, salt and pepper noise. So why this noise is added is to apply the median filter, and then clear that noise. Okay, we have externally added the noise here, and then we removed that noise, and we got this as a final image. This is the filtered image. And when we apply Harris corner detection, some green dots will come. Good feature corner detection, some green dots. And for SVM, proposed SVM, some green dots. And for proposed ANN, okay, corner detection, some more green dots will come. Wherever there are green dots, those are corner detected. Okay, corner detected features. So this figure 15 shows us the image corner detections in a captured image with noise probability is equal to 0.01. Okay, so we can observe here mean square error is 40, PSNR value is 32.09 dB, entropy is equal to 5.09, and the number of corners in Harris corner detection is equal to 77, and number of corners with good feature corner detection is 46, and from proposed SVM it is 220 corners detected, and proposed neural network corner detection it is 409. And in the same way, for the same kind of strategy, but noise probability is equal to 0.05. We have increased the noise probability. That means more noise is added, and this is the result. Mean square error is 46. 47 SVM, yeah, SVM detection is 225, and neural network corner detection is 406. In the same way, for 0.1 noise probability, this is the statistics. So we'll try to have a comparison. This may be my almost last slide. So performance analysis of proposed corner detection methods for various noise probability. Just now we saw some 4 to 5 slides with the noise probability is equal to very less 0.01, and little bit high 0.05 and more high, that is 0.1 noise probability. So what we can observe here is mean square error keeps on increasing. Okay, with more noise probability, mean square error will be high. Okay, error will be high, and noise signal to noise ratio, kept on reducing, because PSNR is inversely proportional to square root of MSC, mean square error. Here we cite, right? Here we cite PSNR is equal to almost 20 log of 1 divided by root MSC. So in that manner, PSNR, as MSC keeps on increasing, PSNR kept on decreasing, and hence as the signal to noise ratio kept on decreasing, then the noise is kept on reduced here from 0.01, 0.05, and 0.1, and as a result, we can see here more and more number of corners are detected. That means the filter efficiency is more, and that is median filter efficiency is more, and we can see here these are the total statistics from corner detection, Harris corner detector, good feature corner detector, proposed SVM corner detector, and proposed ANN corner detector. So for 0.01, this is the thing. For 0.05, it is SVM corner is 225, ANN corner is 406. For 0.1, it is 227 and 439. So here, what's happening is when we keep on adding noise, okay, the performance of artificial neural network, the performance of SVM or artificial neural network corner detection is kept on increasing. Okay, is kept on increasing, or at least it is at least maintained at a high level. Okay, so because noise is added, it is not getting confused, or it is not showing the less accuracy of corner detection. So more and more corners are still getting detected. So in that way, this table shows us the performance analysis of proposed corner detection methods for various noise probabilities. So I think I have covered my part. So thank you one and all for patience listening of my session. And if any questions are there, you can just post here in the chat section of this Zoom session, or else you can just contact me through this email ID, santoshmherur@gmail.com, or you can just give a call to this number so that I can still answer for your questions on image corner detection. As far as image corner detection, image processing techniques are there, I can just give some clarity.
So thank you, Santosh sir. Sir, we have some questions in the chat box.
Okay.
Can you please look onto the chat box?
Yeah. GUI in MATLAB is easy. Yeah,
So
GUI in MATLAB is easy, and also in OpenCV. Like I worked in OpenCV by writing Python code. That is also very easy only. We can have both options. Yeah, GUI is from which software? Like in OpenCV, we can create, and also in MATLAB. So what are the criteria for selection of filters? Yeah, so like I explained one non-linear filter, right? So there are a variety of filters. So among that, if we have a deep study, so we can come across that the median filter will give us more better results. Okay, more efficiency will be exhibited by median filter. So we can choose that. Other than that, also we can again choose any non-linear filters, because noise will be random. It will be non-linear. It will be not a linear one. So better to choose non-linear filters. I think Only these are the questions, sir.
Dear participants, any other questions or queries?
So, lot of papers are available on image corner detection. Lot of papers are there. We can have more literature review on image corner detection. Like today, I just gave some glimpse of image corner detection as a part of image processing and application. In the same way, already people used to know what is edge detection, but this image corner detection is also in place. So if we detect more and more efficiently the corners, then it will be more efficient for all the camera-based applications, even for medical imaging or to detect any kind of diseases in plants or in human body. We can go for corner detection algorithm implementation to any applications of camera. That's all from my side, sir.
Thank you, sir. Shall we wind up, sir?
Yeah, please. If there are no questions, anyhow, participants can take the screenshot of this slide where my mail ID and mobile number is there. They can approach if any queries are there in future.
Dear participants, please kindly note the mail ID of Dr. Santosh Herur, sir. If any queries, please you can contact with him over the mail. Okay. On behalf of our department and SDM Institute of Technology, I want to express our heartfelt gratitude to Dr. Santosh Herur, sir, for enlightening us during this faculty development program. I hope all the participants
Thank you,
have
sir.
got
Thank you very much.
very good insights from your sessions, sir.
Thank you, sir. It's all my pleasure.
Thank you, sir. Thank you very much.
Yeah, I also thank all the participants for joining to the session and making this successful. So hope to hear you all soon. Thank you all.
Thank you, sir.
Recording stopped.